Recording then. So perhaps you can see my screen. Okay. So we will today we will be talking about goodness of fit test. Okay. So there will be hmm. So as you remember, um, I I told you. So this is the scenario when you have a single hypothesis. Let's call it the null hypothesis, uh, called the H0. So you have a single hypothesis, and this H0, okay, and it is sometimes called the null hypothesis. And you have data. So this data I use as the x vector, which is essentially the n-dimensional uh, column vector or row vector. So I have n measurement of this x variable, and you want to make so the goal is uh, you want to make a quantitative statement uh, about the extent of agreement between the data and the hypothesis. Okay, so this term is very important. This is a quantitative statement. You want to, it's not a qualitative statement. It's more or less agrees or it does not agree. It's not a statement of that kind. The statement needs to be quantitative because we want to assign a number to the extent of agreement to your hypothesis. The way to do that is to, so the way we define it uh, mm, is by we define something called a p-value. So the p-value of a hypothesis, so the definition, uh, so the p-value of a of a hypothesis that is H0 here, okay, is defined as, is equivalent to the probability, okay, of find let me write the symbol here, probability of finding the data as bad as the observed data, uh, or even worse, given the hypothesis true. Okay, so this is, so this symbol that I have written here, here uh, this is the probability of observing uh, data as bad as the observed one, or even worse. Okay, I will try to explain what I mean by this. Okay. So suppose in the in a coin tossing example, uh, the example I gave you is that suppose in a 2000 um, in a 2000 population school, there are 800 girls and let's say 1200 boys. So suppose uh, 2000 population, then there are 800 girls and 1200 boys. Okay. And I asked you um, how compatible is the hypothesis, uh, how compatible is this data with the hypothesis that there are equal probabilities of finding girls and boys. Okay. So we ask, so this is my so this is my data. So I want to ask how compatible is this data with the hypothesis that they that they are that let's say girls or boys are getting equal chances. Okay, so this is my hypothesis here. So this thing that girls and boys, the relative fractions would be equal, is my hypothesis H0, and I have to make a quantitative statement of how compatible is this data with this hypothesis. So then I basically calculate uh, this p-value here, p-value for this hypothesis. It tells me so p-value how it is defined. So p-value is defined as the probability of observing X as bad as the observed data. Why is this bad? Because I am looking for uh, a possible set of data that has even worse compatibility with the hypothesis than the observed data. Now, uh, let us try to figure out what is the uh, what is the equally worse thing that could happen. So, on the other hand, it could happen that you get 1200 girls and 800 boys. This is also like equally, this is basically the other side of the coin, so it is equally worse. Or even worse would be what? So, if my given hypothesis H0 is that there are equal fractions of girls and boys, then the worst compatibility will be that you get fewer than 800 girls or even fewer than 800 boys. Okay. Those will be even worse. Okay. So then P is the probability of all those things happening together. So remember, so the probability of observing X number of girls, so would be N Cx, then this is half to the power x times half to the power n minus x. Okay, so this is my hypothesis. This is the H0. This is the probability to observe x girls. Okay. Now I have to. So this is the probability to observe x girls. Okay. Now I have to compute the probability of observing fewer than 800 girls or greater than 1200 girls, because those are equally bad. So what I need to figure out, that this is, let's say, this is, you sum it, either x equals 0 to 800 and plus the same thing, x equals 1200 to 2000, the same thing. Okay. Now remember, uh, of course, a more skewed observation. Suppose you have like 500 girls and 1500 boys.
So,
Yes,
so you are taking 800 because it's a first observed data here to make the
this
hypothesis.
this is the observed data. Yes.
Okay, okay.
Okay. So remember, smaller the p value, worse is the compatibility. Okay. Smaller the p value, worse is the compatibility. Okay. So uh, smaller the p value, worse the compatibility of data with H0. Okay. Then if this if this p value is very small, then you say, oh, this H0 is a very bad hypothesis to explain this kind of data, right? So this p value is kind of a measure of how uh, how different is your data from the expected values from your hypothesis. Okay. Now, at what point would you reject this H0 in view of this data? Okay. You will say that the data is so bad. You want to say, after you cross a certain threshold of p, you conclude that this data is so bad that this H0, we can rule out with, say, this level of confidence. I will formally introduce a confidence level at a later point, but you can try to figure out a cutoff of this p value when you say that this data suggests that this H0 is not the prevailing hypothesis to explain this data, and we are observing a new effect. Okay. So so if this, let's say, p value is too small, this too small, I will quantify what I mean by this too small. Then we will say that we are observing a new effect. Of course, we do not know what this new effect is, but this is a new effect uh, that is not captured by H0. Okay. Now, how do I quantify this too small? Okay, so uh, how to quantify it? Okay, in other words, what is the cutoff value of p beyond which we'll conclude that there is a new effect? Okay. Now, of course, there is no given hard and fast rule on where to put your cut on the p value before you conclude that there is a new effect. Okay. So a traditional way to do this is to assign some sort of a significance to this new effect. Okay. So uh, we can define the significance of the new effect. You can define the significance from the new effect using the p-value. Okay. Now, how do I define the significance of the new effect? Okay. So this is the significance of the new effect. The rule is, first you draw a standard Gaussian or a unit Gaussian. So suppose this is my Z and this is my phi Z. All right. And the unit Gaussian will look like this. So it's the Gaussian distribution with mean at 0 and sigma equals 1. So this is my unit Gaussian. So it's mu equals 0 and sigma equals 1. That is the Gaussian. So this is basically it is a normalized version of the Gaussian function. Uh, so it does not matter. All right. Now suppose you have observed, so you have observed data and you have a hypothesis in mind. So you can calculate the p-value and this p-value returns you a number. Okay. This p-value, since it is returning you a number, now you can ask, this is a pertinent question, that you can ask what value of z, let me call it capital Z. So this is the value of Z that I call, let's say, capital Z, after which the area under the curve this amounts to the p-value. Okay. So this is the area is equal to p-value. So if the p-value is smaller, you have to go to higher extreme of Z. So remember, this has sigma equals to 1. So this has sigma equals to 1, let's say. So suppose this is sigma and sigma equals 1. So in the Z axis, you are kind of moving in units of sigma. Okay. So if you are this Z equals capital Z away, then for a usual Gaussian, for a general sigma, you will say that you are Z equals Z sigma away. So you have to go to Z sigma away to get uh, the uh, the data as compatible or even worse compatibility with H0. Okay, so this kind of translates very well to the significance. Remember, lower the p-value, the farther you have to move on the right hand side, and you are moving very far from the mean. Okay, so if your p-value is very low and you are kind of sure that there is certain new effect, and to quantify the significance of the new effect, what you do, you find out the p-value. So this p-value is basically, now according to your definition, p-value is 1 minus phi z. So the total area is phi, and sorry, the total area is 1, and the area on the left is the cumulative distribution up to z, right? So this is my capital phi z. This is the cumulative distribution function for unit Gaussian. Okay, so this is So this phi z is the cumulative distribution function of unit Gaussian. This is the cumulative distribution of the unit Gaussian. Okay. And then basically you can solve it. So basically phi of z, this capital Z, is 1 minus p, and this significance z would be the inverse function, the inverse cumulative function of 1 minus p. Okay, and then you find this z. Okay, so uh, so then you say that the significance of the new effect is z sigma. So your conclusion is in the
Sir,
context of the
this is phi of z or phi into z? Like how area means phi of z is not area, na? Dimensionally, unit area. One is this unit area, na? P
oh
is equal to
this
one.
this is, then I made a mistake. So this is a small phi.
Okay.
So the conclusion you draw from this is uh, the significance of the new effect is z sigma. Okay, so this is the conclusion you draw. Okay, now uh, what is the value of this z before you claim that you are substantially away from this hypothesis H0, and uh, so let me write this down. So what is the value of z before you claim a new discovery? That is, you are observing uh, sufficient deviation from H0. Okay? So from the null hypothesis, you are observing sufficient deviation. In particle physics, uh, we use this z to be greater than equals to 5. That is, unless we have a 5 sigma significance, we it's a very conservative estimate. So uh, unless we have a 5 sigma significance, we do not um, claim a discovery. Okay? I'll show you examples. That's why I opened that note there. Now, you might wonder, if I want to have z equals 5, then what should be the corresponding p value? So you would be interested to know that z equals 5 correspond to p equals 2.9 into 10 to the power minus 7. Okay, so kind of uh, so you are observing a data, the probability of which emerging from the hypothesis H0 is of order 10 to the power minus 7. It's minuscule. Okay, so that you need to be that confident before you claim a discovery. And in particle physics, we are very conservative and try to
Sir,
claim. Yes.
we want P to be large, right? If P is small, then we say that the hypothesis is bad.
Yes, that hypothesis is the H0 is not the correct hypothesis. We are observing something new.
Okay, but here p is very small, right? 3
Yeah, that's
into
why we can confidently say that the 80 can almost never be true.
okay,
We are observing something new.
okay.
Hello, sir.
Yes.
Sir, in 5 sigma it covers almost all the area, na? In 3 sigma we are focusing on it covers 99% of area. If you are saying that is 5 sigma, then there is very less chance of new discovery.
It's 99.9 maybe, or 99.999999. But there is still a finite probability.
Then you can say there is new discovery in that region.
Yes. So this is, but we have to. There will always be a finite probability, right?
Okay. Yes. Yes.
So you have to stop at some point. So in particle physics, we stop at z equals 5, and which correspond to p equals 10 to the power minus 7. Okay. In
Okay.
medical physics, when human life is in question, you have to be even more sure. Perhaps the p value needs to be even small before you conclude anything statistically significant. So it depends on field to field. In at what point you you consider this p value to be sufficiently small to claim that you have observed a new effect. Okay.
Yes, sir.
All right. Any other question?
So,
Yes.
sir, if we have to means uh, start the theory means the hypothesis, so that's also come from some data. So here we are checking that
No, hypothesis doesn't come from data. That's why it's a hypothesis. Hypothesis doesn't come from
then
data. You have a theory for this thing. For example, go back to this example of girls and boys in a school. So you have a predefined hypothesis that you are expecting that the girls and boys ratio will be 1. That is what your expectation. Prior to doing the experiment, you have a
yeah,
hypothesis. So you want to test in your country whether girls and boys are treated in equal footing. And you are looking at this data. Now, in view of this data, what can you conclude about your hypothesis?
okay, then we have to find the p value according to the data and
Yes.
the theory we have chosen.
Then you have to make quantitative remark about the extent of compatibility of the data with your theory. Okay.
Okay, so let's say if we have two theories and they are nearly compatible, then you have to choose which one is better. That we have done in the first part, I guess.
That's sampling of data. That is a
Okay,
different
okay,
problem.
okay.
Okay. That is a different problem, and this is a different problem. In statistical point of view, this is a different problem. Here, you do not have an alternative hypothesis. Okay. And in the first example I gave, you had two hypotheses, H0 and H1, and more often than not, you assume that one of them must be true. Okay. Suppose you are observing a track inside your detector. It can either come from electron or from pion. Nothing else. Let's say in the world you are living, there are only electrons and pions that are ionizing this thing. Okay. So you know that that track can come from only electron or pion. There is nothing else in the world that can give you the track. So that means you have to choose one or the other. Now you have observed a track length, then you are choosing one or the other. Okay. Now, in this second example, you are considering that there is a hypothesis. Let's say that is I have only observed electrons. Okay, in my world, I have no observations of pions or anything yet. Okay, but I do not know whether such exotic particles can exist or not. Now, you are suppose you are running your experiment for a long time and you are observing many of tracks. Okay, sometimes then you observe a track that does not behave as an electron should behave. Then you say that I think I have discovered something new. You do not specify what that thing is. That is the thing. So you are saying that you have observed a data which is not captured by your standard hypothesis, that means you need to expand your theory space. You need to try theories other than this H0. Okay? So that gives you a hint that you should try different hypotheses. Okay? So this hypothesis is not good enough to explain this data. It does not tell you which hypothesis is true, by the way. I'll give you examples in a short while. It does not tell you which hypothesis is true. It just tells you that the given hypothesis is bad. Okay.
So it's also possible that you make some changes in your hypothesis and then it's compatible with the data.
That is not allowed.
Okay.
It's not. You are missing the main point here. H0 is a simple hypothesis. That means it has a well-defined prediction.
No, I'm saying after the finding the p-value and you find that it's not compatible with your data, then can you try to change your hypothesis and then?
That's a different hypothesis.
Okay.
Okay. Whatever change you make, that's a different hypothesis. Okay. So in terms of statistics, when you are thinking in terms of statistics, it's not that your hypotheses are continuously evolving. I mean, it can, but that's a different type of problem. Okay. So here we have very different hypotheses. Okay. So here in this case, actually, I have only one hypothesis with no alternative hypothesis. I do not know what is true. Suppose I do not know suppose you are looking for a theory of dark matter. You have constructed a model of dark matter and you are testing data with that particular model. Okay, and that data did not agree. Let's say with more than 5 sigma significance. Then you do not know the theory of dark matter. Okay, at all. You just say that theory of dark matter is not true. You cannot say anything else. Okay. You are not making any claim about which one is the correct hypothesis. You are just saying that the given hypothesis is not very good. No more, no less. Okay.
Okay, sir. Yeah.
You are not, remember, when you are testing goodness of fit test, you are not making any claim about any alternative hypothesis. Okay. You are just basically weighting the data in view of a given hypothesis. That's it. Okay. All right. Now,
By rejecting this hypothesis, I mean, in papers we see that they often make some bounds on some data. So
those are different again. Those I
okay,
will come.
okay,
Okay. You are not placing any hypothesis. Okay.
okay. But they consider models. So those are hypotheses, right?
Those are different kind of hypotheses. Those are called
Okay,
compound hypotheses.
okay,
Try to distinguish between hypotheses. These are simple hypotheses where no parameters are unknown.
okay.
Okay. Everything is determined. Remember, if your job instead, for example, suppose, so here you went to judge the data in view of a given hypothesis. But instead, what could you have done is that suppose you said that probability of finding girls is, let's say, theta, and probability of finding boys obviously will be 1 minus theta. Now, given this data, what is the most probable value of theta? That's an entirely different kind of problem. Do you understand my point here?
Yes, sir.
Okay. So that is a very different kind of problem. That's the problem of parameter estimation. Here I have basically, in a sense, I have infinite number of hypotheses depending on the value of theta, and I am trying to figure out what is the most probable value of theta. But it is not what I am doing here. I am saying that I have a given hypothesis, given simple hypothesis, which makes very definite prediction. That means I have chosen a value of theta. This theta equals half, and I am testing how much that hypothesis is compatible with this data. Okay. That's what I mean by goodness of fit test. Hopefully that is clear by now. All right. Good. Now, let me give an example. Okay. So, what time it is? 16:11. Good. So suppose a typical particle physics example. Again, I am sorry that I am talking about particle physics, but you can try to figure out some examples from your field of study, and I will be interested in hearing that. Okay. Please try and do that. That how this analysis can be relevant to you. Okay. Let me talk about the discovery of the jet boson. Okay, then I will give you an example in here as well. So the discovery of jet boson. I should not say that it is jet boson here because this test does not allow me to actually say whether it's a jet boson or not. Okay. Now the way to do that is that you collide E plus E minus. So suppose there is an electron beam that is coming from this direction, and you have a positron beam. It was that's coming from this direction. So this was done in lab, which is a large electron positron collider. Okay, and you are trying to look at two muons. Okay, so that you collide E plus E minus, and they annihilate, and then they produce two muons. Again, people who are not from a particle physics background, I apologize that, but hopefully you will get the gist of it. And so it tells you that this process can undergo, in as long as this LEP is concerned, okay, in two ways. Okay, so in particle physics we talk about mediator particles. Okay? So this mediator particles can either be photon or a jet boson. So this let's say, again, for non-particle physics, do not pay much attention. So you have electron here and you have muons here. If this jet boson theory is true, then the mediator can be gamma or jet. Okay. Now suppose this jet has a mass which I did not know previously, let's say, but now I know. So let's say 90 GeV. Okay. So again, people with non-particle physics background, you consider this as gram. Okay. So jet has a mass of 90 gram. Okay. This sounds stupid, but anyway, let's assume this is a mass of 20 gram. So suppose you want to test whether there exists a jet boson or not. Okay. So whether there exists a jet boson or not. Okay. By the way, this data, this E plus E minus to mu plus mu minus, the data for the cross section is available in many reviews of lab physics. So you can actually see the plots. Okay, if you are interested, and I strongly encourage you to actually look at the plots and extract the data and do the computation with that. And if you can complete the computation, then it will be very nice, and you can show it in the next class. And I will be interested in looking at it. So essentially what happens is that E plus E minus collide, something like something happens in here, then you get mu plus mu minus. And how you measure it? You measure it as the cross section of E plus E minus going to mu plus mu minus. Okay. And this cross section you measure as a function of this mu plus mu minus mass. Okay, the how much mass does this mu plus mu minus carry together. Okay. Now let me not talk about mass. Let me talk about energy. How much energy is mu plus mu minus carry about? So this sigma, so this cross section is kind of a function of the energy carried by. So it depends on the energy carried by the muon pairs. Okay. A muon pair. Now to look, how do we see this thing? So this cross section essentially tells you that if you are shooting uh, n number of particles, n number of e plus e minus pair. Suppose you are shooting 1000 e plus e minus pair. Okay, then you multiply this 1000, roughly speaking, with this sigma. If you can calculate this thing, you multiply this thousand is called the luminosity of this E plus E minus collider. Like, what is the flux of this E plus E minus? Again, ask your experimental friends to explain this thing, and if they cannot, then you can curse them. Okay, but so this is essentially the luminosity. In layman's terms, is how many E plus E minus are participating in the collision. And this sigma is that what fraction of those are being converted into mu plus mu minus pair. Roughly speaking, that is essentially true. And the the particle physics theories basically calculate this part. So we can do clean calculation on how this thing behave with the energy carried by the muon pair. Okay. If we cannot calculate by hand, we can always simulate, but that's a different thing for now. But so this has a this comes from a theory prediction. So suppose I am colliding 1000 E plus E minus pair, and I know this, and if I plot the energy carried by mu mu, so this is kind of vague writing. Actually, it's the invariant mass, but you understand what I mean here. So this is the energy carried by mu mu pair, and this is the number of mu mu events. Okay, if you plot this, then you have two hypotheses, right? So one hypothesis is that if Z was absent, and another hypothesis is that Z is present. Okay. Now, of course, the way I have done the goodness of fit test, I have only a single hypothesis, and the single hypothesis is, so this H0, the hypothesis I want to test, that there is no Z boson. Okay. So if there is no Z boson, that is, this process is only mediated by this photon, then this cross section will have a structure, and if it has a Z boson, then this cross section will have a different structure. I want you to understand that. Okay. So suppose H0 is that there is no Z boson, then this cross section, the functional dependence on this energy, you can calculate from particle physics theories, and you can do a theoretical plot of that thing. So this is it. Okay, so this is how your mu mu event, how much it is compatible with that. Okay, number of mu mu event is compatible with that. Now you notice, so now you actually do the experiment. So this is my H0 prediction. This is a quite robust prediction because I already know quantum electrodynamics and I know how to calculate these things. So this is a prediction. Now you basically go and measure, and you measure basically a histogram. So your detectors have energy resolution, so it can resolve energy, let's say of 20 GeV, I'm assuming, or 10 GeV. So you see number of events between let's say 0 to 10 GeV, you see this many number of events. Okay. And you see in 10 to 20 this many number of events, okay? And so on and so forth. Like I am doing it really nicely here, but this might not be as beautiful as this. Maybe I will show you one actual plot how these things looks. And this is basically 0 to 10, 10 to 20, 20 to 30. And when you come to let's say 90 to 100, okay? 90 to 100, okay? So this there you observe this many. And as you go move in the next, you get this, then again. So you kind of get the idea. So this yellow ones are your data, okay? Now you already had a prediction from your theory. So that is the purple line. So purple line already told you that how many events per bin should you expect. So that is the area under the purple curve. So for example, for this bin, the expected value was kind of this, and you are seeing very close to that. So there is no reason to suspect. All right. And then but you see that in this particular bin, so this little thing are called energy bins. So this is how your energy is kind of binned in this level. You see that in this particular bin, call it the 90th bin or the 10th bin, okay? So this is my 10th bin. You see that in this bin you expected at an average this many events, okay? And you observe this yellow thing. All right. So you now suspect that at least in this bin there is something happening that cannot be explained by just photon only, okay? By just photon only. And you want to quantify the severity of this disagreement, okay? Like how significant is this bump over here, okay, compared to this thing. Traditionally, this purple thing is called the background, which I will call write BKG in small. So this is my background, okay? All these things basically the background prediction. So this is the background in the 10th bin, in the 10th bin, okay? So similarly, in every energy bin you have a prediction for the background, okay? And you kind of want to see whether you are observing a new effect over the background, okay? So your H0 is that there is nothing new other than photon. So then you have an estimation for the background, okay? And you have an actual data, and you want to make a quantitative statement about how compatible is my data with the background only hypothesis. That is, there is no jet boson, okay? Or there is nothing except photon, okay? So like how compatible is the observed data with the background only hypothesis, okay? Does everyone at least get an idea about the question I am asking here, okay? Is this clear to everyone? Okay. I hope it is. All right. Yes.
Sir, was Higgs also discovered similarly?
Any statistical statement about any discovery is made in this way in particle physics. Okay. I will
It,
show those
it,
plots.
it was also discovered in lab.
No, no, no. It was not discovered in lab. Lab was
Okay.
very close, but it was not. That is a different story. Okay.
Okay.
It's not discovered in lab. Discovered in LH. Anyway, so yeah, I am choosing this data because this data is particularly clean. This E plus E minus collider data are really clean. Okay. Now, phew. Now let me plug in some numbers, some fun numbers that we wanted to play with. Okay. Suppose this background event, this average number of background event, I have to predict it. I call this nu b. That was 0.5. Let's say the average number of background event that was 0.5. Basically, the area under the small curve. Okay. And this yellow event, this yellow thing, this is basically n observed, and that is equals to 5. So you have observed in this particular bin 5 events whereas if only background was true, only background was contributing this thing, at an average you are only expecting 0.5 events. Now in this scenario, you have to make a quantitative remark that in this particular bin, uh, how well the observed data is described by the background only hypothesis. Okay. So remember, as I told you in the earlier classes, the distribution of the number of events in this bin would be governed by a Poisson distribution. Okay. And the Poisson distribution, so the Poisson distribution is f of observing n events. Okay. This is given, there is a signal event, average signal event nu s and nu b. So that would be given by nu s plus nu b by factorial n in e to the power minus nu s plus nu b. That is, if both my signal and background are present in a certain scenario, let's say, this would be my distribution, the Poisson distribution that would govern. So this is the Poisson distribution that govern the number of events in a certain bin. So if I am considering only background only hypothesis, that means nu s equals 0. So I am testing background only, that I am assuming how compatible the data with the background only hypothesis. Then this simply becomes nu b to the power n divided by factorial n e to the power minus nu b. Okay. So remember, first of all, I have to assign a p-value to this. How do I assign a p-value to this phenomena here? So if I now try to construct a p-value here, so the p-value will be, so this is equivalent to probability of observing n. Remember this again. Remember the definition of p-value. That has, yes,
Sir, can you explain what is mu s here?
nu s is the average signal event that I am expecting.
Okay.
Remember, so p is the probability that my observation will be as bad as the observed one or even worse. So you are expecting 0.5 events and you observe 5 events. What could have been worse if you observe more than 5 events? Like when you are testing your background hypothesis, what could have been worse for that? So if you have observed more than the number of observed events, so the total probability of n greater than equals to n observed. Okay, and what is that? So then basically it is the sum of n observed to infinity, because Ponzo is a discrete random variable ideally. A for observing n, then nu s equals 0 and nu b, for some nu b. Okay, so this is, and now if you plug in the number, so you actually take the complement of this distribution. So it is basically, since the total sum is 1, so you can write it as 1 minus this is n equals 0 to n observed. I got to put n equals n observed. Then f n nu s equals 0 nu b. Okay. Now if you actually plug in the number, so now if you plug in, put n observed equals 5 and new background equals 0.5, then you should get this p value, that is the probability of observing n greater than equals to 5 given my signal is 0 and my nu s is 0 and nu b equals 0.5. Okay, so this is approximately equals to, I have crunched the number, it's 1.7 into 10 to the power minus 4. That is the p value. And if you try to invert it to the significance of this thing, so this z is basically the phi inverse of 1 minus p, that will come out to be 3.6. So you will say that this disagreement, although it looks very large, that I am jumping from 0.5 to 5, is only a 3.6 sigma effect. Okay, so you say that this effect, so this effect, so you say this is a 3.6 sigma effect. That is, the background only hypothesis is incompatible with the data with a significance of 3.6 sigma. Okay, it is not enough to claim a discovery. It is not enough to say that we are observing something new. Okay, does everyone understand this statement? How can you practically apply this thing?
So, okay, so what can we say here? This is just a error that we are observing here because something is going on at that area.
Yes, I mean, if something is, so it is a very good hint that if we accumulate more data, the significance will increase. It is telling me that there is something new going on that deserves our attention, but the significance is not enough yet to claim it's a discovery. We have to accumulate more data. Okay, so as the data increases, you will see that if you multiply this both these things by a factor of 100, then this significance is going to increase. Okay, so if you use more luminosity, more energy, if you acquire more statistics, then this peak will become more pronounced. Okay, so that means that there is a chance, basically there is a 10 to the power minus 4 there is a probability of 10 to the power minus 4. What did I write this here? That it is a statistical fluke. It is small, but it is not small enough that I can rule it out. Okay. Is that clear?
Yes.
Yeah. So what you can do actually, what experimental physics people do, they convert this type of plot. This is the basically the background event. The purple histograms are the background event, and the yellow ones are your observed data. They can actually calculate the p-value bin by bin, every bin. Okay, and just below this plot, they can plot another thing. So let me erase this part here. So just below this plot, what you can do. So here again you have E mu mu, and here you have the p-value. Usually it's the local p-value, and bin by bin. So suppose this is 1, this is p equals 1. Okay, and usually it's plotted in the log scale. So if it is 1, then it is like 10 to the power minus 1. This is 10 to the power minus 2. It's 10 to the power minus 3. Then 10 to the power minus 4, and so on. So this is log scale, and this is the p-value equals 1. Now again, E mu mu has these small bins and so on. Okay. So on this part, apart from this small region, everywhere my data is kind of uh, agreeing with the background only hypothesis. Okay, that is only photon. So if you actually take the p-value data, then here you will get values close to 1, okay, but slightly less than 1. But as you move close to this point, your p-value will start to fall, okay? And maybe here and then here, all right, and then again, yes. And if you kind of connect this, then you will see that it looks like this, and that means that in this region, uh, something new is happening. Okay, so something new is happening. So in this particular region, from this p-value plot, so here something new is happening that cannot be explained from a background only hypothesis. Okay. In the same way, you can also plot the significance. So this significance that I have calculated, where did I? This is the 3.6 sigma. Okay. So you can also plot the significance as well. Okay. So you have there are many ways to represent this kind of data, and this significance I am intentionally writing. This is a local significance. Okay, so that is in terms of sigma, and then you will have a plot. So near 90, E mu mu equals 90, you will say that the significance is kind of bumping up. Okay, so this is kind of 3.6. Okay, so if you plot the local significance here, so that means that there is a in this 90 GeV bin around this, there is something new happening that cannot be explained by the photon only hypothesis. Remember, in all these statements, I am not saying anything about the jet boson. Okay. I am just testing the hypothesis if there was only photon and there was nothing else. First, let us try to fit the data with the background only hypothesis. Background you define properly, and you see that there is something new that is happening with a certain significance. And if you find that, and if you find such a new thing somewhere, okay, then you can try to invoke alternative hypothesis. So this testing does not tell me anything about alternative hypothesis. So this significance, so this difference, can it be explained by jet boson? Can it be explained by something else, or so on? There can be many other hypotheses as well. I have to test those hypotheses. That's a different thing. So which hypothesis fits this better? But at least I am making this claim that if I am subscribing to photon only hypothesis, the data does not agree very well to that particular hypothesis, and p-value or local significance are a good way to test whether a certain hypothesis is true or not. Okay. Now, I talked about this local significance. By the name, you might notice that there can be something called global significance. Okay. So the global significance, in a way, so remember, when I calculated significance, I only considered this bin, the 10th bin here. Okay. Because there, from my visual appeal, it has the largest discrepancy with my expected background. Okay. So I am basically visually biased to pay particular focus into this bin. But suppose I want to remove such bias, like bias in not in a very technical sense, but in literal sense, that I want to close my eyes. I want to analyze all these bins, and I want to have a measure of the global compatibility of the observed data in all these bins with the observed data. So I have all these purple boxes here, and I want to have a quantitative measure of the data being well explained or not well explained by this when I am considering all these histograms. And from that, I want to gauge how much globally significant is this pattern from the background only hypothesis. So the way to do that is to do something called a Pearson chi-square test. Basically, what you do is that you construct a chi-square function. Okay. And this chi-square, so if you have capital N number of bins, okay, so this I equals 1 to n. So this n is the number of bins. So bins in a very general sense here. That means the number of data samples in a certain way. Okay. And then here you have ni minus nu I whole square divided by nu I. Okay. So this ni is the observed data in ith bin, and this is my expected data in ith bin. By expected means, in this case, if you are testing background only hypothesis, then it is the average background events, so average background events in ith bin. Okay. So remember, in general, the chi-square definition was x minus mu whole square divided by sigma square. Since the average of a Ponce variable is the variable itself, that's why I've kept it here. And the standard deviation of a Ponce variable is the square root of that average. So if you square that thing, this sigma square becomes as nu I. So this, this is the chi-square, and it tells you how much the data globally deviates from the expected value in each being. So more this deviation, and all this deviation basically add up because I am adding the squares of every being. This is the observed data, this is the expected data. If the observed data are very much different from the expected data, then uh, this will sense that difference, and since I am adding the averages, those differences will add up if I sum over all the bins. So it kind of gives me all the errors. Okay, and in the limit that these new i's are sufficiently large, everything goes to a Gaussian distribution. So of course this will follow a chi-square distribution with n degrees of freedom, as we have learned previously. Okay, so since this goes as a chi-square distribution with n degrees of freedom, so this is a chi-square distribution with capital N degrees of freedom. And then if you define the p-value here, so how will you define the p-value here? So suppose you have done a measurement, okay, you have a particular value of this ni. So remember, you want to integrate or you want to sum over from the point that is as bad as the observed data to the region that is even worse compatibility with the compared to the observed data. So how does chi-square gives me a measure of worse compatibility? So higher the chi-square, worse is the compatibility. You remember? Because if all these ni's are kind of like equal to nu I, then you will have very small chi-square, like ideally chi-square equals 0. And more is the deviation of each ni from this respective nu i's, the worse it is. Okay. So basically you integrate from this chi-square observed. So whatever ni you have observed, you chi-square observed to infinity, because this region gives you worse compatibility. Okay. So again, so if you basically your with n degrees of freedom, if you plot this, the plot will look like something like this, right? I'm not drawing it correctly, like this instead. So on towards the right, these are worse compatibility. So if your chi-square observed is somewhere over here, so if this is your chi-square observed, you want to go to the right, so that this gives worse compatibility. Worse compatibility with H0. Okay. So if you integrate this stuff over here, and you take the chi-square distribution, so this is f of z with n degrees of freedom dz, and that gives your p-value, and then you convert it into significance. Okay, so now you can convert it into significance, and this is your global significance. Okay, and a thumb rule is that a global significance would be a little bit less than the local significance, because in the local significance what you are doing is that you are handpicking that particular bin with the worst compatibility with the data, or with the hypothesis. So you are basically cherry picking your bin. But when you are trying to gauge the global significance of a new effect, what you are doing is that you are considering all the bins, all the energy bins And in some of them, the data is kind of uh, well explained by the background because the signal is not significant there. So since you are also including those effects, like those bins where data are more or less agreeing with the hypothesis, that means when you talk about your global significance, so global significance is a bit less if your hypothesis is not wild, really, like you have a difference in all the bins actually, uh, then you will have always global significance to be somewhat less than the local significance. Okay, so these are kind of the theoretical aspects of how to do a goodness of fit test. So in summary, you have a hypothesis H0 that you call a null hypothesis, and this H0 makes well-defined predictions, the completely measurable predictions, and you have data. You are comparing the degree of compatibility of this data to the given hypothesis H0. To do that, you are defining first the p-value. So smaller p-value gives worse compatibility, and smaller p-value you can convert it into significance. Okay, and after you convert it into significance, then you can make a quantitative statement that the data features new effect that is not captured by by my uh, by my hypothesis H0, and the significance of that new effect is that times sigma. Okay, and in particle physics, the extent beyond which we are confident enough to call a discovery is 5 sigma. Okay, now at this point, anyone with any questions?
Can you give the background of chi-square? Why we need this thing?
So this chi-square is a quantity that you construct when you try to assign global significance, when you take into account the effect in all the beans. That's it. Okay. So in a single bean, you know that the data is Poisson distributed. But if you want to take the effect of all the beans, then uh, how will you able to uh, do that? So that's why you construct this chi-square variable, which takes into account the discrepancies in all the beans.
Okay. So I was just thinking, can't we just take the bins that are closer to the anomalies? So that will give. I don't know
Uh,
why we are taking just all the elements, all the bin sides. So I was just thinking, is it possible to take the bins that are closer to the uh,
yes,
anomaly that way,
actually,
and
that's what is done. So basically, I'm discussing this separately. So basically, what they do is that you actually apply a cut. Okay. So first you try to distinguish signal from background. So suppose you have a cut over here. Okay. So you have, suppose this is E cut. Then you basically focus on this region. That is usually what it is done. Okay. But if you apply no cut, then you have to take all these things into account. But usually there are kinematic cuts that does not take into account literally all the bins, but the bins in the neighborhood of this new effect. Yes, but you need a valid reason to do that. That's what I mean. Okay.
and yeah, and sir, there is some range for chi-square. Can we explain that?
What, this region of integration?
No, So the chi-square value, how is there any cut for chi-square value?
Um, I mean, see, here you have constructed the chi-square. So in other way, if you want to reject this hypothesis, then you can apply a cut on this P. Okay. So suppose you want to reject this hypothesis at a 95% confidence level. That's the usual game. So you have to find out the chi-square cutoff that gives you this 95% confidence level corresponding to area here. And if your chi-square observed is greater than that, you reject the hypothesis. If you want to just accept and reject the hypothesis. Okay. So in that way, you can use your chi-square cutoff for this. So that was discussed in the during the chi-square lecture. Okay. When I discussed the chi-square distribution. Yeah. So that was like I used the example of an ice cream parlor and so on, if I remember correctly. That was discussed there. Okay.
Yeah. Okay. Thank you.
All right. Now to show you some actual data, that's why I have opened this. So this is the Cesare Bini lecture note that I also linked in the Google Classroom, so you can find it there as well. Okay, so you can, and you can should also check the references. Okay, so you can scroll down here to, I guess, page 53 or 54 maybe. Maybe this one. This is the discovery of lambda b0. Okay. By the way, Kamalji, you were asking about where to find the data. So these are the kind of data that you can use to try and sample your signal from background. Okay.
Yes, sir. Yes, sir.
Yeah. Let me come to this discovery plots. Here. No. Here. Okay. So he has not put the Higgs histogram here. All right. You can now see this data. Okay. So this is the 2011-12. This is from this paper, physics letter B716 2000. Yeah. So this is the discovery of the Higgs boson, by the way. This is the buzzword. Like this was one of the most famous plots around 2012. And let me see if this is the local significance over here, and so on. What is the background and signal? Did he anywhere put that background and the signal? Confidence level that Higgs had ruled out. This is the confidence level on mu. It's a signal strength plot. All right. I cannot find this thing, but I have to. Okay, let me focus on this plot and let me open that particular paper, the Higgs discovery paper. Observation of a new particle in the search of the standard model. Let me open the archive version because it is freely available. You see, this is the Higgs discovery paper, one of the papers that got the Nobel Prize. And you can see that almost after 2012, every paper on particle physics actually cited this paper. And I don't know why it is so slow. Yeah. So, okay, the inspire link is not. So it says 12,000. Oh, it's crazy. All right. So you come to this thing. Can everyone see this with proper zoom effect? Atlas detector. Yes. So suppose this is the Higgs goes to Z standard 4 lepton channel. Okay. So what you have is kind of, even if you do not understand these things, you will see plots like what I have shown. Yeah. Yeah. Events for 5 GB M34. That is not very. Yeah. This one. So you see. So you see there it is kind of an energy plotted along x-axis, and that is the events for 5 GB. So these beans are of like 5 GB width. I mean, it might not look like 5 GB, but you see this black dots are 5 GB width. Okay. Now see what is happening. If there was no Higgs, so what are they observing? They are observing 4 leptons. Now people who are uh, uh, not familiar with particle physics lingo, try to think about this in this way. So electron is a lepton. Okay. So suppose you are observing 4 electrons. Okay, 1, 2, 3, 4. Okay. So you are colliding basically protons. Okay. You see, and uh, you see this 4.8 femtobomb and 5.8 femtobomb. So these are basically luminosities. In my notes, I told you that how many E plus E minus are you colliding. Okay, so this is like 1000. So the counterpart to this 1000, okay, is this thing. So this is kind of a measure of how many how many colliding particles are there. Okay. Now, since you know the cross section of this finding these 4 electrons in the final state, in the detector you will observe 4 electrons. So you train your detector so that whenever it sees 4 electron, it clicks, and if it sees something else, then uh, it goes away. It does not click at all. All right. So it basically tells you that. Even if there were no Higgs, so you consider a hypothesis, which is basically a scenario, things that we know, usually we call it standard model, okay, and it is without the Higgs, standard model without the Higgs. For people who are aware of particle physics, they will make a sense of this thing. But for people who are not familiar with particle physics, you assume that it is the world without the Higgs boson. Okay. Now, in a world without the Higgs boson, the electrons will still exist, right? It can come from different sources. Different things can radiate electrons and so on and so forth. Okay. So, uh, so the red, for example, this red is basically a background jet star. That is, uh, if the Higgs, if the Higgs was not present, even then these red things will come. Okay, so you will see that many. So this red comes from the cross section calculation, in this case simulation. So this red things basically tells you that even if my Higgs were not present, my 4 lepton would come, and they can come from this thing. Okay, and they can come from this source also. So this is another source of finding 4 electrons. Okay, whatever this means. Okay, this is another, the purple thing is also another source of this also. Forget about the Higgs as of now. Forget about the Higgs. All right. Now you say that now you actually do the experiment, and this black data, this black dots with, of course, their uncertainty. That's basically, the black dots are really the observed events. Okay. So basically, in this in this little area, the observed event is this, in here it is this, and in here it is this, and so on. And suppose you want to explain this black data, all right, with the hypothesis that there is no Higgs. Okay. Now, if you try to do that, then basically you have to calculate the local p-values. One thing you can do is that you can calculate the local p-value in the same way you have learned to calculate local p-value. So this, up to this red bar, basically it is the background. So this is your new B. It's kind of you read it from this plot. It is a new B, and this one is the black one is observed. For now, just concentrate on the center thing, on the central thing. Okay. So they are observing it in the 4 lepton channel. It's in the 4 lepton channel, and this is the data, and this is the background that they have observed. All right. Now, if you do a p-value analysis, let me see if they have given this plot. They have do many, and this is another gamma channel. The plot is really interesting in that channel as well. Yeah, this is the gamma irreducible background. Let's forget about that. Do they give the p-value? P-value. Transverse energy plane to WW star. Statistical procedure. They explain this thing here. They do a multivariate analysis. But we can do a simple-minded analysis. Here you go. This is beautiful. Okay. So concentrate on the Higgs to Z star. All right. Here. So this is the channel we looked into, right? And this thing here. And if you see the p-value analysis here, so the p-value analysis, so on the x-axis you have the energy scale. So this 115, 120, 125, 130, 135, and so on and so forth. Okay. And if you do that p-value analysis, so this black will be again data. Okay. This black line will be again data. Then you see that near 125 in this around in here, the p-value has dropped to 10 to the power minus 4. All right. Okay. So here you see there is something new that is happening in here. So the p-value has dropped from there. So you get this plot, you get this local p-value, p0 value plot from precisely this this particular plot. Where did I have that? Yes, this particular plot. Okay, so you see something new at near in this bin. Okay, and you do the p-value analysis. Okay, now you also see that data in this region are also kind of misbehaving here. So can this be a new effect? Because here I am observing only seven events, and here actually I am observing I don't know 13 or 14. Okay, so and the degree of discrepancy is kind of the same, but here comes the statistics. So it kinds of fools you that there is also a kind of a new effect that cannot be explained by this red thing. But remember, here I am asking what is the probability that a background event which is as low as 2, so this is 0, 1, 2, so this background is over here, is as low as 2, that will jump to 7. And here I am asking a background that is as high as 7 itself, 6 or 7 itself, and that will jump to 12. Now if you actually calculate the probability of 7 jumping to 12 is much higher than probability of 2 jumping to 7 here. And that's why you will see that the p-value in this bin is much higher, or actually much lower than this one. So this is not significant enough. And if you go back to this plot again, okay, blah 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 blah. Where do I have this? Here. If you go to the plot, you see that thing here. You see there is a small effect. The p-value dips, but it's not very significant. It's only 10 to the minus 1. So it's 1 in 10 chance that it can be a statistical fluke. But here it is nearly 10 to the power minus 4. Okay. Yet, if I only look at H2ZZ star, I cannot be sure that this is sufficiently significant to claim a discovery, because it is 10 to the power minus 4. The p-value is 10 to the power minus 4. Okay. Now, so I see that even though this is much more statistically unlikely, I see that there are kind of two effects where the background actually does not agree with the data. Now, is this pattern repeated in other channels? For example, in Higgs to gamma gamma. Okay, so this channel, there also you do a similar study. So you will see that in here probably. What is the H to gamma gamma channel? Event selection here. Okay. So this dashed thing, the black dots are of course exact data, and the dashed thing was just the stipulation for background. The background, if you fit a fourth order polynomial. Okay. Signal background, you forget about that. So you only concentrate on background, the dashed line. Okay. And this is your data. So remember the scale here. Okay, events per 2 GeV. Okay. So here in this bin, for this black dot, which is, I don't know at what, at 125, the expected was 2000 event, and actually you have observed 2300 or something like that. Okay. So you have observed 2300. Okay. So quite a large deviation. Now you actually try and assign a p-value to that, and then in the neighborhood, and so on and so forth. You do such things. So this plot is after reduction of the background, but to do the p-value you have to come here. Okay. So then so you basically see this many events. Okay. After you have an idea about the background, like how many sources photon can observe, and then you do the same kind of analysis. Okay. You do the same kind of analysis. You calculate the local p-values. Where was it? And you see this. So you again see that here actually here they have not done a nice job. So you see that 5 sigma means 10 to the power minus 7, the one that we already calculated. So this is the threshold for 5 sigma. But in the gamma gamma channel alone, the significance that we are observing something new over the background is not yet 5 sigma. It is around 10 to the power minus 6. Okay, in the data. Okay. But once you combine this with this, okay, like statistically combined in the same way, like doing chi-square or whatever, you combine these two measurements, like bin by bin. Okay, and then you can do this local p0 value here. It's kind of a global. You see this? This is combined search results. Okay. And then you see the p0 value drops to 10 to the power minus 9. Okay. This is the 10 to the minus 9. So it has dropped beyond 5 sigma, and in that review, actually, if you observe the significance, the local significance corresponds to it, it is around 6 sigma. So now you can be confident that whatever is causing the effect here, it does not agree with the background only hypothesis. By background only hypothesis, I mean the world without the Higgs boson. So I have a simulated data, like the expected data, uh, like the red plots. Okay, those are my expected data. Where is this? What did I open my paper? So this red thing it comes from theoretical calculation. If the theory is very complicated, it comes from simulation. So I knew that if there was no Higgs boson, then I was expecting this red histogram over here mostly. But I am observing the black ones, the black dots here. So now I can assign bin by bin, I can assign the p-values, and I can convert those into significances, and I should get a plot like that. So now your homework is this. Your homework is basically you take this plot, okay. Again, apply your again G3 data, this plot and the Higgs to gamma gamma plot here, and do it yourself now with the Higgs to gamma gamma. Where is my Higgs to gamma gamma? Signal modeling, background modeling, systematic uncertainties. Yeah, and you take this plot, this red plot, let's say. Okay. And you can also take the blue plot if you fancy. It's the same thing. It's just a weighted plot. Okay, and you from those two plots you obtain those the final results. Maybe where is this? Well, you obtained this and this. Okay? So you note down the article number is 1207.7214. I will not force any non-particle physics people to do this, but people who are doing particle physics, at least you take those two plots and convert it into these plots and try to understand the meaning of these things. Okay, and concentrate on the black plots for now, and we will try to figure out what the others mean actually. And so this is your first step towards understanding experimental paper for people who are trying to do theory and experimental paper. And people who are not from a particle physics background, I strongly urge you that you try to figure out if you can map this analysis into something of yours. If you have seen p-values calculated somewhere in some certain context, try to figure out. And if you want to share your experience, I'll be very happy to actually see that. And then I will also learn in that process actually. So what kind of data people in other fields are analyzing. Okay. So with this, it might be a good time to close today's session. Now let me know if you have questions. Okay. Did you understand the Higgs discovery paper? How many of you did understand how Higgs was discovered? Now, should I start a polling? Okay, let me. Okay, I can now stop recording, I guess.